And there's also a help session here at 1. I sent an email out about to it. Did y'all get my email about it? Yeah. It'll be in this room at 1 o'clock. It's really for the 101 class, but it might be helpful for y'all too. I think we ended with that. With what? Yeah, the free response where we had to do the dot product. All right. Well, y'all look away for just a second, okay? Y'all see that? Those are the answers. Oh, you haven't written down, don't you? Right. I'm sorry. Okay, so each of the blocks in this figure moves to the left. Now remember, our work is equal to F dot D, and the dot product is defined as the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle theta. Now, on Wednesday when we did that quick test, we actually did the dot product. So we had our vectors that were in vector notation, so they were in I, J, and K notation. And so we actually did the dot product between those two vectors. But if you just have the magnitudes of the vectors, it's going to be the magnitude of the first times the magnitude of the second times the cosine of the angle between them. All right, so that's sort of a general definition for work, FD cosine theta. Now, that tells us that if our force and our displacement are in the same direction, if they're in the same direction, that means that theta equals what? What's the angle between F and D if they're in the same direction? It's equal to 0. So theta is equal to 0 degrees, and cosine of 0 is equal to 1. All right, if they're in opposite directions, then theta is equal to what?
180.
180, right. So if they're in opposite directions, theta is 180, and the cosine of 180 is equal to what? It's -1, right. And if they're perpendicular, that means that theta is equal to 90 degrees. You have to remember the symbol. It means at an angle of 90 degrees, perpendicular. All right. So theta is 90 degrees, and the cosine of 90 degrees is equal to what? It's equal to 0, right. So that tells us then that if our two forces or my force and my displacement are in the same direction, it's going to do positive work because that cosine of 0 is +1. If they're in opposite directions, right, they're anti-parallel. That means they're parallel to one another but in opposite directions. Then that's going to be negative work. So what is a force that is often opposite the direction of motion? Friction. So the frictional force will most of the time do negative work because the force of friction is in the opposite the direction of motion. And if they're perpendicular to one another, as we'll see in a few questions, they'll do no work at all. So if the force is perpendicular to the direction of motion, then it does no work at all. So that's like the bucket of water or this notebook. You extend the force in the vertical direction, but then you move it in this direction. So the force is up, but the displacement is to the right. Then that does no work at all. So with that, which of these forces does no work? That would be the force that is perpendicular to the motion. They're all moving to the left. Which one is perpendicular to the motion? A, right. So this force does no work. All of these objects are moving to the left. Right, so this force does no work. Which force is doing negative work? C is doing negative work because the force is in this direction and the displacement is in that direction. Let me write this down. So C is doing negative work because the force is in that direction and the displacement is in that direction, so that's negative work. This is doing no work because the displacement and the force are perpendicular. Which force does positive work? Okay, B does positive work because the force and the displacement are both in the same direction. But I also had that this one does positive work. How is that the case? That's right, Daniel. It is moving to the left, and then it also has a component of that force that is to the left. So this force has a component, Fx, that is in the same direction as D. So more specifically, the x component of that force is doing positive work, and then the force that does the most work is going to be, well, the most positive work is going to be B. All right. Why don't we, I'm just going to go and give you all those. So go ahead and click in. The first one was no work at all, just for the sake of your clicker points. No work at all is, which one was that? Oh, that was A. So number 1 was A. So we're looking at 1 right now. Just a few more seconds. Number 2, what was number 2? Which force does negative work? That was C, right, yeah. So just a few seconds. I'm telling you the answers. Alright, we're missing a couple folks. Alright, I'm going to go away. 22. What's that? Oh, we'll just do B. So 3. The one that does positive work, we'll say is B. Alright, just a few more seconds. We'll stop at 12. And then which force does the most work? The most positive work. Now, forces on B and C do the same amount of work, but one is actually taking away energy, and one is giving energy. So which force does the most work? That would be B. Okay. I'm not sure if we've talked about this. Let me go back up and look for a second. Yeah. So negative work means taking away energy. So remember, work is a scalar quantity, right? And so whenever we have a negative, it doesn't mean that it's in the negative direction, because it doesn't have a direction. It means that you're taking away energy. So if something's moving and you apply a force to it to stop it, that means that you're taking away its kinetic energy, and that means that you've done negative work on the object. Okay, when you lift an object, do you do A positive or B negative work? That's the question. A positive or B negative work? And then the next question is, does the gravitational force do A positive or B negative work as you lift an object? Okay, just a few seconds, I'll take away that first one. Stop at 22. And then the next one, does gravity do positive or negative work? So when you lift an object, you do positive work because your force is in this direction and your displacement is in that direction. Does gravitational force do positive or negative work? Very good. So the gravitational force here, you're acting against Fw. So Fw is down, D is up, so it does negative work because that angle is 180 degrees and the cosine of 180 is -1. Okay, let's try this. The shopper, supermarket, pushes a cart. As we've talked about, you should really do what? Pull the cart, right? Like this. Y'all try this when you go shopping? Did you? How was it?
Not good. Probably those are the ones that turn.
Well, this class says it's difficult to turn.
Yeah, it's very, very wide turns. I try at all expense not to use a shopping cart.
Huh?
So I try at all expense not to use a shopping cart.
Right. If I'm for other people there, so we usually get 2 shopping carts when we go to the grocery store. Split up. All right, let's do about 10 more seconds. Stop at 155, 155. Very good. Or B is the right answer. Really just sort of plugging in the right numbers here. Here we have the magnitudes of the vectors, F and D, and then we also have the angle between them. So our displacement is in this direction, our force is in this direction, and there's an angle of 60 degrees between them. Right? You can imagine our grocery cart here. Okay, that's a pretty good grocery cart. And those forces are acting upon it. And so I just plug in those numbers here. I have a force of 40 newtons, a displacement of 25 meters, and cosine of 60. It's the angle between them. That's 1,000 times a half. That's 500 newtons. Or excuse me, 500 joules or 500 newton meters. All right, let's do a few of the quicker questions. Have we done any of these? I don't think we have we? No. Now, when we go to the grocery store, listen, if y'all care, like sometimes we'll go early in the morning. Like sometimes I'll go like at 4 o'clock in the morning if I go to Walmart because they're open like all night, and I'll get 2 carts and I'm like pushing the carts like this, and then I pull out. They just have one cashier open at 4 o'clock in the morning, where you buy cigarettes and alcohol. Y'all might not know that. They just have one cashier at 4 in the morning at Walmart. And so I have to put all of my groceries on that little bitty table. The lady hates me for it. Because they don't have a belt, right? They just have that little table. I don't know if y'all care about that. Apparently not. All right. All right, is it possible to do work on an object that remains at rest? These should be in the back of your book. I think it's like 30 something. What is it, Michael? 288. All right, so a few more seconds. B is right. So if it's at rest, that means the displacement is 0. So even though you might be applying a force to it, the force is doing no work. In order to have work, you have to cause motion. A box is being pulled across a rough floor at a constant speed. What can you say about the work done by friction? A few more seconds. So 25. B is right. Friction almost always does negative work, but in this case, if I'm pushing it across the floor with a certain force in this direction, I have a displacement in that direction. The frictional force is opposite the direction of motion, and so these two vectors are opposite one another, so the work is negative. And friction usually does negative work. We'll see one case where it doesn't. Can friction ever do positive work? The answer to this is A. I'll explain in just a second. It can do positive work. When I was a kid, we used to ride on the back of the truck on the tailgate and hang our feet off the back. Y'all ever do that? Yeah, I think you get arrested for that now. But so if you imagine the back of the pickup truck, it's not a very good pickup truck. And here I am, dangling my feet off. I'm laid back, relaxing. The force due to friction here is in this direction. Right, the frictional force is actually what's holding me onto the truck. What is the direction of the displacement? It's in the same direction. So this is one example where you can have friction actually do positive work. So it's actually the frictional force that is causing you to move. Otherwise, if you didn't have the frictional force, you'd do what? Just slide off the back of the truck when the truck accelerates forward. So there are instances where friction can do positive work. In a baseball game, the catcher stops a 90-mile-an-hour pitch. What can you say about the work done on the catcher by the ball? Think about what work is. It describes giving energy or taking away energy. Okay, right now we're sort of evenly split between B and C. So think about this. I have this ball. This ball has a certain amount of energy. And over here I have the catcher. There's his mitt. And when he catches that ball, it takes away that energy. And what does that mean in terms of work? If I do something to take away energy, what does that mean in terms of work? Y'all are stuck between B and C. Do I do negative work or do I do zero work on the ball? Right, but the catcher is doing something to the ball. Right, the catcher is stopping the ball. All right, so a few more seconds. I'll stop at 130, 130. All right, B is right. It does negative work. You can think about it in terms of, like I said, the catcher is taking away energy from the ball, so that means he's doing a negative work. That's what the negative means. Or you can think about it in terms of the force and the displacement. The force is opposite the direction of the ball's displacement, right? The force is in that direction while the ball is coming this way. And so I have a negative work being done by that force. The ball is tied to a string, being whirled around in a circle. So I'm doing like this, like a lasso. What is the work being done by tension there? So it looks like this. What's the work being done by tension? Where the tension is this force. Okay, just a few more seconds. Check everybody's in. Okay, very good. A is the right answer. Why is A the right answer? It does no work. Right. There is a displacement, right? It's moving, but the displacement and the force are perpendicular. So my displacement at any one time is tangent to the circle. So my displacement would be that direction, not down, but out of the page. And my tension is perpendicular to that always. We'll get into that in circular motion, which we'll get to in a couple of chapters. Let's see, what does a lawyer always wear to work? It's a joke. You just say, I don't know what. A lawsuit. Alright, you lift a book with your hand in such a way that it moves up at constant speed. While it is moving, what is the total work done on the book? So you have two forces at play. I want to know the sum of those works. And stop at 55, 55. Let's see. Let's try this again. So I have two amounts of work that's being done. I have the work being done by this force and the work that's being done by this force. And what I'm asking here is what is the total work? That means what is the sum of all the works that's being done, right? So I have a certain amount of work being done by this force and a certain amount of work being done by this force. If I add them up, what then is the total work? This could also be restated as what is the work done by the net force. All right, so let's try that again. Up till now, we've been talking about what's the work done by an individual force, but here we're asking what is the work done by the net force, the total force. So I'll stop at 25, 25. No. F hand plus mg. No, that's not right. D is the right answer. The reason C isn't the right answer is because one of these is negative. So if you wanted to make C the right answer, you could say F hand minus mg, and then that would be the right answer. But since this is moving up at a constant speed, what is my net force? It's 0. So my net force, my acceleration is 0, so my net force is 0. And that means that the total work that's being done is also 0. Follow me on that? Yeah. Did I select the right answer for the previous one? Okay. Okay, we'll come back to this. We're going to go into kinetic energy right now. Okay, so kinetic energy is the energy of a moving particle. Or a moving object. And it can be any moving object. We won't get into thermal physics, but as I said, when you go into thermal physics in your PChem class, you'll talk about the classical view of thermodynamics and how you can view moving molecules or particles of a gas and how that can describe the thermal properties of a system of a gas. Now, we sort of alluded this to the last thing. First, I'm just going to give you the expression for kinetic energy, and it's just 1/2 times the mass times the speed squared. So this is the speed, not the velocity, so there's no direction associated with that. And as a result, the kinetic energy is going to be a scalar quantity. You'll want to know where this comes about from. Remember, we said before that the work is equal to the force times the displacement. Where let's say that more generally that this is the force in the x direction times the x displacement. So taking that in the same direction, or the parallel vectors. If that force changes as a function of position, then we want to write this as an integral. So we'll say now that work is the integral of f of x times dx. Now we'll see this in questions a little bit later, where our force changes as a function of our position. So depending upon what our x position is, the force will be a different value. And so we'll describe that force as a function. F of x is equal to x squared plus 3x plus blah, 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 whatever. All right? And then if we want to know the total work that's done, then we'll take the product of f and x as it changes over that function. And we'll see some examples of that later, where we actually have to do that integral and calculate the total work done over a certain displacement. Okay, so I can say then that this is the integral of m times a times dx, where a is in the x direction. But if you recall, a is defined as what? What was the basic definition of the acceleration that we hinged all of our kinematics equations off of? D something something. Change in something over change in. Right, it's our acceleration is dv dt times dx. So I can rewrite my integral in that way. However, I see here dx dt. What is that equivalent to? Dx over dt. dv. Right, or actually not dv, but this is just equivalent to v. if you remember our velocity, we defined as dx dt. Right? We defined our acceleration as dv dt, and we defined our velocity as dx dt. You remember those definitions? Those were our two basic definitions that led into those kinematics equations. Those kinematics equations just came from these two very basic definitions. So all of our kinematics hinges on these two definitions, which are pretty basic. So I can rewrite this integral then as the integral of m times v times dv. mv dv, excuse me. All right, the mass doesn't change. All right, so this is the m integral of v dv. And if you remember, when we're taking the integral of a to the, or excuse me, I'll write it as v to the a dv. That's going to be v to the a plus 1 over a plus 1, right? The integral of a polynomial. I know some of you aren't in Calc 2, but you'll recall how to do these, the integrals of polynomials? Yeah. Okay, if you don't, you'll need to know how to do that. So you can just revisit that calculus review, just the integrals of polynomials. We're not going to do any funky integrals, just straight up polynomials. All right, so this then would be what? The integral of v dv. Where this is assumed to be a 1. So I would take a to be 1 over here. V squared over what? Over 2. All right, so this is m v squared over 2, which is 1/2 mv squared. So that's where we get this expression for our kinetic energy. It just comes about through the integral of the work function, f dot dx, or f dx. I think in Calc 3, do y'all do the integrals of the dot products as well? Okay, we're not going to do that here. We'll assume that the force and the displacement are in the same direction. We'll see some questions like this later, and very likely you could see a question on the test like this. And you look back at the old test where you have to calculate the work done by a force that varies with position. So we'll see that a little bit later. Let's see, Emily de Châtelet is just sort of an interesting character in history. She lived in the 1700s, about the same time as Voltaire, during the time of the Enlightenment, when there were a lot of scientific progress made. She was French. She showed that the kinetic energy is proportional to v squared. And people didn't believe this before because they believed that squared numbers were evil. So prior to this, people of the time square numbers were evil. And then they didn't believe that something in nature, right, could not be described by a squared number because God wouldn't create something that was dependent upon a squared number, because squared numbers were evil. Now, y'all might think squared numbers are evil too, right? Do you? No. But it was kind of silly for them to think that squared numbers were evil. Why would that be? Because they used squared numbers quite a bit back in the 18th century. What did they use them for? In 18th century France. What did people do in the 18th century largely to live? They did what? They were farmers, right? Because they had to grow their own food, and they couldn't go to Walmart at 4 a.m. and buy 2 grocery carts full of food. They had to grow their own food, and most of their time was spent farming. All right, and so why would farmers need to use squared numbers? Right. Yeah, so if they want to know their yields, their crop yields, which is important to know because you want to know how many crops are going to get you through the winter or else you'd die, then they had to calculate then what was the area of their fields and how many crops would they actually yield from those fields. So they used squared numbers a lot. So it's kind of ridiculous for them to think that squared numbers were evil because they used them a lot. But anyway, they did not believe that kinetic energy was proportional to v squared. Instead, they believed that kinetic energy was proportional to v. Obviously, we know that that's not true, and it's because of the work that she did, where she took a ball and she dropped it into a clay surface, and she dropped it in such a way that she found that it had a velocity equal to v, and it dropped a certain amount. All right, and then she would measure the height h, or the depth that it made into the clay. And then she would drop another ball, like a steel ball, from a certain height, such that it had a velocity 2v. It's a little more complicated than this, but let's just say that if it had twice the velocity, what do you think the height or the depth would be? If I had a depth h on this side with a velocity v, what would my depth be on this side? Not twice, but what? All right, it's v squared, so it's going to go 4 times as deep. So over here I'll have a 4h. All right, 4 times the depth, because my kinetic energy is proportional to v squared, and if I double that, I 4 times the amount of kinetic energy, which gives us 4 times the depth. It's a little more complicated than that, but not terribly much so. All right, so she showed then that this kinetic energy was proportional to v squared. I have a little clip about her. She was just a fairly interesting person, I think, because she was different. There weren't many women scientists at the time. Now there are a lot more, and obviously, I mean, a lot more women in higher ed as well. But for her, it was quite a big deal. So let's listen to this. It's just a couple minutes. It's just sort of about her life, of course. Okay, let's do this quick test. It should be pretty, hopefully it's simple. This object is thrown like this. I want to know the kinetic energy at the top of the trajectory. A lot of you are missing something on this question. The part that you're missing is that at the top of the trajectory, there's only one component to the velocity. Remember, we have the x component in that direction, but remember the y component at the top is equal to 0. So you need to find the velocity at the top of the trajectory. So rethink your answer. A lot of you have it wrong. Only one of you has it right, actually. Alright, looking a lot better. A few more, let's go up to 3 minutes. Just a few more seconds, I'll stop at 2:58. C is the right answer. It's 1/2 mv squared. Alright, but as I said, this is going to be Vx because there is no velocity in the y direction, so that's 1/2 of 0.2 kilograms times Vx, which is 35 cosine of 30. That whole thing is squared, and that gives us 92 joules. So 92 is the right answer. All right, let's talk about the work energy theorem. The work energy theorem, we've already said this in short, but the work energy theorem says that if you do work on an object, you change its energy. So if you do positive work on an object, you increase its energy. And if you do negative work, you decrease its energy. If you do positive work, you increase. If you do negative work, you decrease its energy. All right, let's do some more of these clicker questions, and I think we'll probably wrap up with that. We'll see. We might come back to conservative forces. Okay, so by what factor does the kinetic energy of a car change when its speed is tripled? If I triple the kinetic energy, or if I triple the speed, what happens to the kinetic energy? Let's stop at 45. D is the right answer. It's a v squared relationship, quadratic, so if I triple the velocity, I have 9 times the kinetic energy. Okay, car 1 has twice the mass of car number 2, but they have the same kinetic energy. How do their speeds compare? They have the same kinetic energy. So you can think about their ratio of their kinetic energies is equal to 1, right? They have the same kinetic energy. So if car 1 has twice the mass of car 2, how do their speeds compare? All right, I'll stop at 105, 105. Oh, good. Pretty good. Yeah. B is the right answer. Let me show you. So first of all, we could just say which one's going to go faster, right? Is it car 1, which is car 1, which is a really big car? That's car 1, or car 2, which is a really little car. Which one's going to go faster? If they have the same energy, which one goes faster? Right, this one's going to be going faster, car 2. So we can get rid of any that don't have that. So that's really just D. We can get rid of D. So it has to be one of those others. But we know that kinetic energy, the ratio is equal to 1. That is 1/2 m1 v1 squared over 1/2 m2 v2 squared. That has to equal 1. So if car 1 has twice the mass, I need to change this v2 so it cancels out that 2 in the numerator. In order to do that, I have to have a square root of 2. The square root of 2 squared is equal to 2, and that cancels out and gives me the same kinetic energy of both. Yeah? It's because of that squared term, that quadratic relationship. Right, let's do a couple more. 2 stones, one twice the mass of the other, are dropped from a cliff. Just before hitting the ground, what is the kinetic energy of the heavy compared to the light? think about your relationship. How is kinetic energy related to mass, and how is it related to velocity? And how do their velocities compare at the bottom of the cliff? Is one larger than the other? Are they the same? Right now you're sort of equally split between two answers. How do their velocities compare at the bottom? That's the question. How do they compare? They're what? How do their velocities compare? They're equal, right? Because they accelerate at the same rate, right? Remember, that doesn't depend upon mass. So they both fall at 10 meters per second squared at that rate, or at that rate of acceleration. So they're going to have the same velocity at the bottom. So how do their kinetic energies compare? All right, I'll stop in just a few seconds. I'm going to stop at 140. D is the right answer. A lot of you had 4 times as much before, but they're going to have the same velocity when they reach the bottom. And since kinetic energy is just 1/2 mv squared, the one with twice the mass will have twice this energy. So E is not the right answer. Okay, well, you've already answered this, but let's go ahead and plug it in. How do their speeds compare? All right, just a couple more seconds. C is right. We'll just do one more after this, then we'll wrap it up. All right, just a few more seconds. I'll stop at 28. Very good. I've increased our energy, so I've done positive work. Let's see, I want to do. Did I do the smell mop joke? I did do that one. Knock knock. Smell mop. Did I do that one? Have I done that one? Oh, I'm sorry. I can't think of another one. Alright. Oh, let's wait. We'll do this one next time. It's a little bit complicated. Alright, hey guys, just want to encourage you that, like, I'm feeling it too, that we're in the middle of the semester, and this is sort of the time that you want to slack off a little bit, and like I want to dismiss y'all at like 7:40, and I want to just not go to class, but I need to just buckle down and just keep doing what you're doing. Alright? 3 o'clock, I want these, please. I'm not in my office, just give them the secretary, put them in my box, so I'm on my door, it's fine. Please give me the exam too. Now, a couple of you didn't give me your exams, that's okay, I've already looked at them, but when you bring me your rework, bring me your old exams too. And I'll return them next week.